Hi everyone, welcome back to the channel. I'm Manisha. Today we are going to see very interesting research study which is on transformer architecture. This neural network based architecture is specially used for the language modeling, and the name of the research paper is Attention is All We Need. So let's get into it. So before to the transformer model, some famous architecture we see in the field of natural language processing, such as a recurrent neural networks, long short-term memory networks, that is LSTM, and gated recurrent unit, that is GRU. So what these models are for? These architectures were particularly designed to handle sequential data, capture temporal dependency effectively. These models are used in tasks for especially language modeling and translation. While RNN, LSTM and GRU have been good in handling sequential data, they present several disadvantages compared to modern architecture like a transformer. So what are these difficulties or disadvantages? So these models have a difficulties with the parallelization, which means that as these model process data sequentially, so each step depends on the previous one, and so it takes a lot of time, computational time, and so leading to longer training times, especially when model is trained on large data set. We also see the struggle with a long range dependency with these models, then complexity, efficiency. There is also scalability issue. So RNN and other models, they tend to be less scalable when dealing with the extremely large data set But for many modern application which requires to handle large data set in less processing time, transformer is the efficient solution. So let's talk about the transformer. What is a transformer? So a transformer is a type of neural network architecture that has become fundamental in the field of deep learning, as we know. This particularly handles a task in natural language processing. We can say it is a revolutionary development in neural network. Transformer introduces a self-attention mechanism that enables the simultaneous or parallel data processing. And what are the advantages that we see with the transformer is that it is outperform over older models RNN, LSTM and GRU. It has a parallelization capabilities, and also it handles large data set, complex data set, and it has high in efficiency. So let's see the research paper which is based on transformer model. So the transformer model was first introduced in the paper Attention is All You Need by Ashish Vaswani in 2017, and this is from the organization Google Brain, Google Research and University of Toronto. So the transformer architecture is divided into two primary components. First one is encoder and the decoder. So encoder layer works on input sequence concurrently, and it involves sublayers as well. And decoder layer consists of three main sublayers. If we can take an example of a machine translation task, so in which encoder process the sentences in the source language, for example English, while the decoder incrementally generates the translation in target language, for example Spanish. And now we will explore the each components of the architecture. So we see that the positional encoding in encoder and decoder, then we see input embedding and output embedding in both encoder and decoder. Then there is a encoder, and this is the decoder, and the last layers that we see, that is linear softmax and output probability. So let's see input embedding of transformer architecture. We want to pass input in English words and we want to translate into Spanish. So what exactly input embedding layer does? It maps each word into high dimensional space where similar words are closer to each other. It transforms input tokens such as words in text into vectors of fixed size. Let's take an example. Suppose sentence is sunset over the ocean. In the context of language model, each word in sentence is converted into vector because machine understand numbers and not the characters, and so we want to translate each word into vector, into number. The embedding matrix contains a unique vector for each word in the vocabulary, and it effectively translating textual information into numeric data, and that can be processed by the model, as I said. For instance, the word sunset from our example is turned into a numeric vector which might look something like this: 0.25, 0.75, or within a high dimensional space. So it means it also captures various semantic and syntactic properties of the word within its dimension. Likewise, the rest of the words such as over, the, and ocean also represented into high dimensional vector using embedded matrix. Now we will see the next component of the architecture, that is positional encoding. So what is the function of the positional encoding is that it adds information about position of each word in the sentence to the input embedding that we saw right now, and it enables the model to understand word order. Why this position is important? So let's continue with the same example, that is sunset over the ocean. In this sentence we see sunset is at first place and ocean is at fourth place. Let's swap these words. The word that we get after swapping is ocean over the sun, and definitely we are not looking for this meaning, and so meaning is completely changed, and that is why the transformer needs to think or to take in consideration the position of the words, and that's why positional encoding is very important. So now we add a special marker to each word that shows its position in the sentence. So we added a positional encoding to each word embedding matrix to convey their position in the sentence. So here in this matrix for sunset we add something like this: 0.25 minus 0.75, 0.50, 0.10 and 1. Let's think that the 1 is a position of the sunset word, and then over has a second position, and then the has a third, and the ocean has a fourth position. So this actually helps the model to understand the order of the words in the sentence, and in summary we can say that positional encoding adjusts the embedding vector to accurately represent the token position within the sentence. And here we also see some formulation, a mathematical formula from the paper. We will not go into it, but I can say that positional encoding adds position related information into input embedding matrix, and we also see this positional encoding at the bottom of the encoder and decoder stack. So let's see what we have inside encoder. So encoder it basically used to process the input sentence that we see before, and it has a multiple identical layers that is represented by an X in the architecture, and each layer has a two sub layers. The first one is multi-head self attention mechanism, and the second one is a position wise fully connected feed forward network. So let's see multi-head attention layer. So this layer is important component within transformer architecture. Imagine the model has a several monitor, and each focusing on different parts of the sentence at the same time, and each monitor, or we can call head, looks at the words and describe how important they are to each other. Means words, how these words are important to each other. So for example, sun over the ocean, one monitor might focus on sunset and ocean, while another monitor might focus on over and the words. So what is the meaning? Actually they calculate how much attention each word should give to each other based on their meanings and position. For instance, the model might focus on sunset and ocean simultaneously because they are related, and creating contextual representation of sunset that includes its relationship with the ocean. So let's get into some mathematical foundation. Here you see the attention equation, this formula is for calculating attention weights. It actually computes how much attention to pay to each word when considering another word. So Q, K and V represent query key value vectors respectively, and each word in sentence is mapped to these three vectors. In our context, Q might be related to sunset, while K and V are associated with over and ocean words. And there is an attention score as well. Then dimension of the key vectors, that is represented by dk. Then there is a max function which is applied to turn the score into probabilities. Yes, here is another formula for multi-head attention. So what exactly it does, it takes the individual attention outputs from multiple heads and combine them into single output. And to sum up, in the multi-head attention layer, the explain process happens in multiple times in parallel, and which allows the model to capture different types of relationships between the words. Next layer is add and norm of the architecture. So each attention output is then added to the original vector, input vector, to preserve the information through the layer of the network, and afterwards normalization is applied to stabilize the learning process. Encoder, that is pointwise feed-forward neural network. This layer is another key component along with the attention mechanism. The transformer uses these feed-forward networks in both encoder and decoder. They operate on each position separately but in the same way. So which means that for each position on the sequence, say for each word in our sentence, the same feed-forward network is applied, but it's important to note that even though the process is the same, each position has its own input and thus its own output. So feed-forward neural network consists of two linear transformation with a ReLU activation in the middle. So let's take the same example, sunset over the ocean. What first linear transformation does, it takes input sunset and multiplies it by weight matrix W1, and then it adds a bias term B1 into it, and this is the first transformation which actually changes the representation of sunset word into a different space. Afterwards, the transform version of sunset is then passed through ReLU activation function. And what ReLU function does, it keeps any positive values as they are and changes any negative values to 0. After ReLU has done its job, the result goes through second linear transformation with a new weight matrix W1 and bias term B2. And this second transformation typically maps the representation back to the original dimension of the model. So in summary, position wise feed-forward networks allows the transformer to learn even more about relationship between words in the sentence, because they can modify the output of the attention layer at each position. Now we will see the decoder part of the transformer. The decoder also consists of layers that mainly focus on generating translated output step by step. The decoder is generating the translated sentence in Spanish one word at a time. It has a similar structure like an encoder, but with the addition of third sublayer that performs multi-head attention over encoder's output. So each layer in the decoder uses both self-attention to look at previous words in the output and encoder-decoder attention to focus on the relevant parts of the input sentence. For example, the decoder starts generating the translation "Puesta de sol sobre el océano." It uses the defined output from the encoder to select which Spanish word to generate based on the context provided by sunset over the ocean. The encoder decoder attention helps to focus on the sunset when deciding how to translate it into Puesta de Sol. Now on decoder stack we also see some other layers, that is output embedding and positional encoding. So talking about output embedding, it is similar to input embedding but for an output sequence. These layers translate each predicted word into vector and adds positional information like we see in positional encoding in the encoder stack. So as the model begins to translate our sentence, for example sunset over this ocean, the word Puesta de Sol for sunset would get its own embedding and positional encoding. Now there are some final layers that we see in the architecture, that is linear layer, softmax layer and the output probabilities. So what exactly linear layer? So this layer maps the decoder's output to the much larger vector with a size usually equal to the vocabulary. And the softmax layer, it converts these scores of the probabilities scores to the probabilities, and the word with the highest probability is chosen as a translation. So the process continues until the end of the sequence token is generated. And what exactly the output probability does? The output probabilities are the final probability for each word in the target language vocabulary that the model predicts for the next token in the sequence. For example, we have a sunset over the sun. The word Puesta de Sol gets converted into probability distribution over all possible next words, and softmax determines that the sobre is the most likely next word in the translation. So that's how the final layers of the transformer work. And there are some applications that we see of the transformers. So transformer models are not just the theoretical model, they are applied actually already in machine translation, also text summarization, and even in identifying the names and places in the text. With this I would like to thank each one of you. Thanks for watching the video. So I hope you like this video. If you like this video, please subscribe to the channel. I also created one video on 1-bit large language model. You can watch that by clicking on I button. I will also leave the link of the paper and the link of my website in the description box. Please check them out and take care, and see you in the next video.